Welcome to Chapter 7, Chemical Quantities and Reactions, and this will be the final chapter of Unit 3. So your Unit 3 test will cover Chapters 6 and 7. This lecture is going to cover Sections 1 through 3, and Section 1 is the mole. A mole is a quantity obtained not by measuring but by counting, similar to a dozen being equivalent to a count of 12 items of any object. Or you could have a gross, meaning 12 dozens, which is 144 objects. Or you could have a few, meaning like 2 or 3. Or you could have 500 pieces of paper equaling a ream. It is used in chemistry to help us relate the number of reacting particles being used in chemical reactions. Because the atoms and molecules are so small, any sample that we can actually use in the real world has so many particles in there that you can't even fathom it. So it's obviously easier to use numbers that are nice and easy to us, ones, twos, threes, and small numbers like that. And so if we convert the total number of particles to actually moles of particles, it becomes a heck of a lot easier. Just like, I guess, in counting, if there's 85 people in a class, you might say there's dozens of people. It's easier to say that. Or, instead of saying there's 733 miles on this drive, you might say there's several hundred miles or a couple hundred miles, whatever. It's, quicker and easier to understand if you use that. The mole is actually defined as having exactly 6.022 times 10 to the 23rd particles. Okay, and so that is Avogadro's number. Amadeo Avogadro came up with this. He understood that there were that many particles in exactly 12 grams of carbon-12. That's where that comes from. And it's arbitrary why it was chosen, but it seemed to be a good number, and it seemed to be a good source, carbon-12, because carbon is, obviously, the source of our life. It's in all of our organic molecules almost. So that's why that was chosen. Now, representative particles, that portion of it just means that it could be anything. So like a dozen could be 12 eggs, it could be 12 cars, it could be 12 people, 12 classes, whatever it is. A dozen is not defined only in the number of eggs. And same thing, a mole is not defined only in atoms. It could be multiple different things. So you could have it be atoms, it could be molecules, it could be ions, electrons, protons, neutrons, so on and so forth. But it could also be something called formula units. Technically, it could be anything. But formula units are used exclusively for ionic compounds. We don't have molecules of ionic compounds. Molecules are these separable entities, the smallest unit of a molecular compound, a compound made up of only covalent bonds. We can take one water molecule and we could isolate that, but we can't isolate just a sodium and a chloride. And the reason is that the sodium is charged. It's a sphere that's charged. All portions of that sphere are charged. And so it's attracted by negative charges on all surfaces around it. Front, back, top, bottom, inside, outside, whatever you want to say. And same thing with the chloride ion. It's going to be attracted by positive ions all around it. in all three dimensions. Okay? So you cannot isolate just this and call it a molecule. It doesn't do it. As it says here in the write-up, it says that they're used exclusively for ionic compounds. Ionic compounds do not have defined particles that you can separate because they are all bonded to each other ionically ad infinitum in all three dimensions. And that just means that it goes on forever in all three dimensions in a sense. So you'd have a sodium, a chlorine, a sodium, a chlorine, a sodium, a chlorine, a sodium, a chlorine, and so on and so forth until you finally reach the edge of that substance. Like if it's a salt cube, at the very edge of it, there's going to be maybe a chlorine that's by itself and nothing to the side of it that's on the outside of the salt cube. But, we're talking so many particles, it's nearly infinity, ad infinitum. It's not really nearly infinity, but it's a huge number. Keep in mind this number right here. If I was to write this out, it would look like this. 602 hextillion, 200 quintillion. Here's your quadrillions, your trillions, your billions, your millions, your thousands place, and then your ones place. That is Avogadro's number. It's extremely huge. You cannot even fathom that. Let me put this into perspective. If you were to take 1 mole of pieces of paper, and I've figured out how thick pieces of paper are, like a copy paper. And if you take 1 mole of it, 602 hextillion, 200 quintillion sheets of paper, and you stack them up and spread them out evenly around Earth, the entire surface of Earth you can cover. And that sounds great. But you can cover Earth in these sheets of paper so many times that mole of pieces of paper would be almost as tall as Mount Everest. So several miles high. It's an insane number of particles, and if the particle is a piece of paper, then you know. And so you could stack a mole of these sheets of paper on top of each other and it would go past the sun by a long shot. Yet we have a mole of carbon atoms that you can fit that in your hand, and it doesn't even look like much because it's only 12 grams. So the size of these atoms are so small, we cannot count them. But if we can figure out how many moles of these are in a sample, we can use that number much more easily instead of these astronomically huge numbers. So that's why we have the mole. So this is just a picture that explains the mole is a measured quantity by counting. And you see here there's 24 cans equals 1 case. 144 pencils is 1 gross, 500 sheets is 1 ream, 12 eggs is 1 dozen. And you could apply these to any object you want. If you had 144 chairs in a room, you'd have a gross of chairs. And there's many other types of counting quantities like this out there, but these are a few of the more widely known ones. All right, so number of particles in 1 mole quantities. You have a mole of aluminum is going to have 6.022 times 10 to the 23rd atoms of aluminum. A mole of sulfur is going to have 6.022 times 10 to the 23rd atoms of sulfur. And so you can see here we've got atoms for both of these because both of those species are elements. Then we have a mole of water, H2O, has 6.022 times 10 to the 23rd molecules of water. We have vitamin C is going to have 6.022 times 10 to the 23rd molecules of vitamin C. And we have those being used because these are both molecules. They're not elements, so we don't use atoms. Sodium chloride there is a ionic compound, so we measure that in formula units. So you just take the ratio of the elements. There's 1 sodium for every 1 chlorine. So how many of those basically chemical formulas are you counting? So for ionic compounds, we use formula units. Example 1. How many molecules are present in 1.75 moles of carbon dioxide, which is CO2? So in order to do this, we need Avogadro's number. We have 1.75 moles of CO2, so I'm going to write this as N equals 1.75 moles. And you don't write the word of, but when you write it like this, that means 1.75 moles of CO2. Okay? What we have also is Avogadro's number, which has the symbol a capital N with a subscript capital A. Avogadro's number, okay? And that's, again, equal to 6.022 times 10 to the 23rd power. And since we have CO2, this is a molecule. And so Avogadro's number will be 6.022 times 10 to the 23rd molecules per mole. Now the funny thing is that mole comes from the word molecule. And so it's like 6.022 times 10 to the 23rd molecules per almost molecule, but a mole is molecules. Anyways, so what we can notice here is we've got moles and moles. This would be in a numerator, even though it's just a number by itself. A number by itself is always a numerator, but that mole is in the denominator. Okay, so if we multiply those two together, those will end up canceling out and leave us with molecules, which is exactly what the question wants us to find. So we can write this as N times N sub A is going to be equal to molecules. So we have 1.75 moles of CO2 times 6.022 times 10 to the 23rd, and it's going to be molecules of CO2 per mole of CO2, and moles of CO2 are going to cancel out. And when we do that calculation, we get, you zoom that over there, get in space here, we get 1.05, and I'm going to go 2 more, 3.8 times 10 to the 24th. And if we look at everything here, we've got 1.75, which has 3 significant figures. Avogadro's number has infinitely many, so our answer is going to be the 3 significant figures, which makes this 1.05 times 10 to the 24th molecules of CO2. It's a 5 there because the 3 next to it makes it round down. Example 2, how many moles of carbon are present in 1.50 moles of aspirin? So what we can notice is in the chemical formula, there are 9 atoms of carbon per each molecule of aspirin. C9H8O4 is what we could say. All right, so that's going to be important because if we have the number of moles of aspirin, let me put it down here as C9H8O4, H8O4. That's 1.50 moles of C9H8O4. And we just need moles of carbon atoms. Now, we don't need Avogadro's number for this because we're going from moles to moles, but we just need to use this dimensional analysis box method. We can just take 9 atoms of carbon per each molecule of C9H8O4. Now, since I have it per molecule, it might look like it's going to need Avogadro's number, and I could do that, and I could say these don't cancel out, moles and molecules, but we're going to have 6.022 times 10 to the 23rd molecules of aspirin, so C9H8O4 per each 1 mole of C9H8O4. And so we'd have moles of aspirin canceling out. We'd actually have molecules of aspirin canceling out, giving us atoms of carbon. But what we also need to do is convert atoms of carbon into moles of carbon. And so what we'd actually do is divide by 6.022 times 10 to the 23rd atoms of carbon per each mole of carbon. So you can see here now this atoms of carbon cancel out. But so does the 6.02 times 10 to the 23rd Avogadro's number. We're left with moles of carbon, and all we end up having to do is multiply 9 by 1.5. And we get 13.5 moles of carbon. And you could say, in a sense, no, I'll just leave it like that. 13.5 moles of carbon.